Good. Okay. Still alive. Ada suara. Tak nampak muka tak apa. Muka yang handsome tu jangan on. Jangan lawa-lawa tu jangan on camera. Nanti orang lain tak boleh belajar, okay? So let's focus on the slide here. Okay, today we are going to continue our lesson on the module 2 or chapter 2 on lattice structure and crystal system. Okay, the lesson number 1 covers in this chapter. These are the learning outcomes. Okay, number 1, you should be able to describe the difference in atomic or molecular structure between crystalline and non-crystalline materials. Lesson number 2, not lesson number 2, the outcome number 2 is describe crystal structure in terms of atom positions, unit cell, and crystal symmetry. And you should be able to describe the 7 crystal system and the 14 Bravais lattice. All right. Crystallography is a study of arrangement of atoms in a solid. Okay, atoms in a solid, they are arranged in a very systematic way. So you need to be able to identify this arrangement. And it is to look at the properties or to relate the properties of material to the structure at the micro level. Okay, micro level is the level where we can obtain a structure from the arrangement for the atom set. And the crystals are made of metal, atoms, molecular, and or ions that fit together in repeating patterns stacked in 3 dimensions, forming crystal lattice that extend in all directions. So why do we study crystallography? Okay, because it is important to determine the inner structure of almost everything. Okay, and to understand how atoms are linked together. And the crystallography actually provides the most relevant information to understand the properties of materials so we can modify them to our benefits. Only by knowing the structure, then we can synthesize the materials. All right. So this guy is actually they call it Curiosity. Okay, it's a rover that used X-ray crystallography. Okay, X-ray crystallography. What is it? Okay, this guy used this X-ray crystallography to analyze soil sample on Mars, planet other than outside our Earth. It was found that the Martian soil, okay, the soil at the planet Mars, the sample was comparable to the weathered basaltic soil of Hawaiian volcanoes. This is the finding. How? By using the X-ray crystallography. Okay, X-ray crystallography bring information that can identify, okay, the elements out there outside our Earth. Okay, the crystallography actually plays a main important role. Okay, because of this crystallography, the scientists identify this and characterize this and give the information so that they can identify, okay, the elements outside our Earth, and they say it is identical based on this identification through the crystallographic or atomic arrangements that also can be compared to the DNA of the genetic code. Okay, like our human body, we have DNA, but for the materials, it has the crystallography that give them an ID. Okay, like us, we have an ID based on our DNA, but for the materials, they have ID based on the crystallography. So if we have unknown materials, we just go and check by using X-ray crystallography, then we get the identification. We can say, oh, this one is aluminum, this one is iron, this one is gold, this one is volcano materials, volcano rock materials from Hawaii, from the Mars, something like that. So that's the reason it is very important. Okay, well, crystalline in nature, it is it's actually is crystals from the words crystallos, okay, which means ice in Greek. Okay, from the Greek language, we call it crystallos. Okay, the first mineral to be called crystal is a rock crystal, which is quartz. Okay. The ancient Greek believed that clear quartz was ice frozen so hard it could not be melted, but actually it's actually a rock. Okay. So every crystal, okay, actually has an orderly internal pattern of atom with a distinctive way of locking new atoms into that pattern to repeat it again and again. Okay. So this is the schematic diagram that shows how the atoms arrange that forming a crystal structure. Okay, it is this example is sodium chloride crystal. It contains Cl, chloride ions, and Na plus, which is a sodium ions. Okay, this cube, okay, a salt. Okay, sodium chloride is a salt. Okay, this is the cube of salt. Okay, how atoms is being arranged is like this. They are being bonded by ionic bonding, and the atom is arranged in the form of crystal structure. Okay. All right. If we look at different types of state of materials, gas, okay, liquid, and a solid, they are different in terms of the atomic arrangement. Okay, if you look at the atoms in the gas, they are doesn't form any crystal structure. It is far away from each other. And so for the liquids, they are slightly dense, but for the solid, it can be it is very dense, but either it is form a crystal or a structure that repeated in periodic manner, or an amorphous condition where they don't show any repetition in atomic arrangement. So these are the difference between gas, solid, and liquid. But in solid, it has a crystal and non-crystal, where we call it as amorphous. Crystallization is a process. Crystallization, okay, is a process in which iron atoms or molecules arrange themselves into a well-defined rigid crystal lattice, okay, in order to minimize their energetic state. So once they are being arranged such a manner, they will become less energetic, or they become stable, or they become calm. Okay. So the smallest building block of crystal, we call it unit cell. Okay, the smallest shape that keep repeating, we call it unit cell. Okay, so the scientists has described the formation of crystallization in the snowflakes. Let me show whether this can be clear or not. Just a second. tak adalah. Nanti I share lah video tu. Play pula dalam argument. Okay, unit cell. So the smallest crystal structure that keep repeats, we call it unit cell. What is unit cell? It is a unit where a unit cell is the smallest portion of the crystal lattice that shows the 3D patterns of the entire crystal, like this. Okay, this is one example of the unit cell for the snowflakes. Okay, it is interconnect hexagonally, right? This unit cell interconnect hexagonally, right? That's shape the framework of molecules. Okay, unit cell repeat in exact the same arrangement over and over again until it's formed the snowflakes. So example, okay, of the unit cell. Just now I have mentioned about the sodium chloride, the salt, okay. So actually the molecule in the liquid, it is before it's form of bonding, they are far away, the atoms is far away, and it will arrange into this periodic manner when it become a solid. And if we enlarge the structure, we can see it is a cubic cell structure. Okay. So another example for iron. Okay. If we look at the atoms of iron, okay, it is being arranged. If we look at the small unit cell of iron, okay, it is this one is a group of unit cell. Okay, this one is a group of unit cell, and the smallest cell, okay, is actually, we can see from here, is coming from a cubic shape of the crystal structure, or we call it unit cell. Okay, like this. And this guy, this one smallest unit cell is stacked together and repeated until it's formed a bulk materials. Okay, so this is the basic, the smallest unit cell for the materials. Okay, the unit cell is the unit which builds up the whole crystal structure by repeated translation along all three spatial directions. Okay, what is it? Okay, it is a 3D, remember it is a 3D blocks. So the entire crystal can be represented by drawing the structure of the smallest identical unit that when stacked together to form the crystal. Okay, the three spatial direction is X, Y, Z direction. But in the crystal structure, we design the space at the three different axes in the unit cell as X in this direction, Y from left to the right direction, and Z from bottom to up direction. So this is the standard unit cell, the three spaces, three-dimensional spaces of unit cell. Okay, the three lattice constant, the length is ABC. A means at the X direction, B means at the length at the Y direction, and C means the length at the C direction. Okay, this is not similar with other subject like a solid or a static. Okay, The X is from the center to the front, okay, and Y from left to right, and Z from bottom to the top. Okay, the three angles is alpha, beta, and gamma. Okay, so they are all defines. This unit cell defines the minimum size of unit cell. So the cube shape, ABC, length, and angle alpha, beta, gamma is the size of the unit cell. Okay, they are all symmetry. So there are different types of crystal structure. Okay, for the unit cell, when it is arranged from one unit cell to multiple unit cell, okay, it will form crystal structure. So when we talk about, I'm sorry, there are a bit delay in this WebEx. Okay, the lattice is actually an imaginary lines that connect between one atom to the other atoms. Okay, for example, if we look at this shape of unit cell that looks like a cube, so the lattice is actually this line, okay, that forming a square shape. Okay, actually, the lattice point is actually the atom itself that connect by an imaginary line, which is called as a lattice. So the types of seven crystal system. There are seven crystal system. Okay, one is triclinic. Second is orthorhombic. Third is rhombohedral. A bit slow in the WebEx. Okay. And then is monoclinic. They are different in terms of the lattice portion and the angle between the lattice. And then next is tetragonal, and next is hexagonal. Okay, and the last one is the cube. The most famous, most widely application, we call it the cube structure. Okay, for this one is a cubic structure will be the basic for we are going to focus on the cubic structure because it's going to be the basic for the determination of or characterization of the crystal structure. Okay, so this for the seven crystal system, the characteristic you can read from here. There are seven different systems, and the characteristic when we talk about the cell constant or the lattice constant, where the length for each lattice at the three different direction, X, Y, and Z, which known as ABC. So if it is cubic, the characteristic of the lattice is A equal to B and equal to C. And this is the angle between the lattice, which is alpha, beta, gamma, is consistent equal to 90 degrees. All right. The choice of the unit cell. Okay. The smallest from this, let's say you zoom into the microstructure and you found these atoms. Okay. Basically, we can observe this structure by using high magnification microscope. Okay. There are special methods to prepare the substances or the metal or whatever the materials to look under this microscope until you get exactly observe the position of each atom. how atoms arrange inside the materials. So let's say you obtain this kind of patterns. Okay, basically we choose based on the ordered structure. Whether we can see, oh, okay, from here there are an ordered structure. So the basic structure we select based on the cubic, and it may repeat the shape, and each atoms play a different role if they change the position. For example, like this one, okay, this atoms has 4 atoms at the corner. Okay. So this basic cell can be repeated as a cube structure, or maybe a different pattern also can be selected. For example, like this one, maybe rhombohedral structure. Okay, like the green lines, or maybe this one. Okay, which one is the best for this material? Okay, there are several possible primitive units. Okay, with the same volume. Okay, which one is the best? Okay, unit cell should be as small as possible. Okay, actually the key is unit cell must be the most basic, as small as possible. Then we can assign them as a we can identify them as the structure of that particular material. So, and it should represent symmetrically. Okay, so between this one, which one do you think it is the best crystal structure for this material?
Cube.
The cube. Okay, good. Why?
Small unit. Small unit.
The smallest unit in terms of the volume, right? Okay. So another example, like this one, due to the symmetry reason, center cell contains additional, sorry, it's a bit delay. Okay, due to the symmetry reason, centered cell contain additional lattice point can be chosen. Okay, this is to describe the crystal in a higher symmetry system of coordinates. So, sorry, it is a bit delayed. Okay, so based on this selection, which one is the best? Rectangular, the yellow one?
Yes.
Yeah, even though it is not smallest, but it is high symmetrical. Okay, so if you compare to the other two, it is if we divide by 4 regions, the blue and the green one is not really symmetry compared to the yellow one. Okay, so 7 primitive lattice point only at the corner of the unit cells. Okay, under retention of the symmetry, we have centered lattice. For example, like this. Okay, base is like similar to the primitive, but it's contained at the one atom at the surface. Okay, if you look at this, this is at the center of the surface. This is another example. Base center means that at the top surface of this cube, it's contained a center atoms, and another one is body center, means there are another one atom at the center of the body, um, phase centers at every faces. Okay, base center is only one at the bottom or at the top surface, but for the phase center at every surfaces. Okay. So initially we learn about 7 primitive. Each category it can even evolve into other subcategory. For example, in cubic we have 3 different cubic system. Okay, the primitive is simple cubic. Okay, this is simple cubic. Okay, where okay, where it has 8 atoms at the corner. Okay, if we look at the primitive crystal structure, okay, at the corner, okay, atom at the corner, how large the portion of the atom at the corner? If we section the atomic the materials into one small cell, okay, what is the portion of the atoms at the corner actually? What is the size? Let's say we cut the materials into one final smaller cell. So what exactly the volume, the size of the atom at this corner? Anybody?
1/8.
1/8. Okay, 1/8. So imagine this is the smallest cell. Okay, like our body, we have our cell body, right? So the material for the metal, for example, the smallest is this guy, okay, which is the cube. All right. So inside the cube, okay, if we cut the material into one smaller size, which is represent one cube structure, crystal structure. So in this primitive simple cubic structure, it's contain 8 for 1/8 portion of atom. So all together, if we total up the fraction of this atom inside one unit cell of a simple cubic structure or primitive cubic structure, it's equivalent to 1 atomic size. Am I correct?
Doktor ulang boleh? Saya tak beberapa faham.
Tak berapa faham ke atau putus-putus ke macam mana?
Tak faham.
Tak faham Alright. Do you need me to explain in Malay? Maybe my English is very poor.
That will help, Doktor.
Okay. So in Malay actually, bahasa Inggeris pula. Alright, sepatutnya dalam bila kita cakap bila kita cakap dia adalah unit paling basic ataupun paling kecil dalam seluruh struktur metal tersebut, okay, ataupun bahan tersebut. Okay, struktur dia paling asas adalah cube, dan dalam bentuk cube primitif ini, okay, bentuk primitif struktur kubik ini, kalau awak tengok struktur dia, dekat corner dia ada atoms. Tapi bayangkan atom tersebut kita dah cut into 8. Okay. Cut into 8. Dekat setiap corner ni ada 1/8 bahagian atoms. So bayangkan dalam ni ada 1/8 bahagian atoms. Okay. So ada 8 dekat corner tu. Setiap corner tu hanya mengandungi 1/8 bahagian atoms. So bila kita total up ke 8 bahagian 1/8 bahagian tersebut, so dia akan menjadi 8 kali 1/8. So bila 8 kali 1/8 bermaksud dalam unit cell tu, bila kita translate dalam bentuk isi padu, of course, isi padu apa? Isi padu atoms kan? Nak quantify, maksudnya kita nak mengira size. So size dia bagi unit cell tu adalah bersamaan dengan 1 unit atoms. Berapa banyak atoms yang ada dalam tu. So bayangkan kalau awak nak kira bilangan atom di dalam unit cell tersebut, it is 1/8 atoms multiplied by 8. So size ni sangat kecil. Unit cell ni kalau kita translate dalam bentuk isi padu atoms, dia hanya represent 1 isi padu atom. Size sebiji atom. Alright, faham tak?
Okay, faham Doktor.
Faham.
Alright, number 2, the base centered atoms, okay? Alright, sama juga, it is similar to the first one. It contains 8 atoms at the corner, but if we slice it into a cubic shape, so it's only occupy inside the cube. Inside the cube, the portion of the atoms at the corner is equivalent to 1/8 for the size of 1 atoms. So at the corner, there are 8 corners, and the portion of the atom inside the cells, okay, that coming from the 8 corner is equivalent to 1 atom size. Okay, that's only the portion coming from the corner. But there are another portion atoms, okay, obtained at the face, base face, okay, the top and the bottom, okay, the top and the bottom, okay. And actually, imagine if, okay, you can see here it's being written 2 faces multiplied by half size of the atoms. So kenapa half? Why is it half size of the atoms? Why it is half? Not quarter, not 1/3. Why is it half?
Because we put it based on top and bottom face.
I know I know it is very logic to have half size at this point, okay, at the bottom and at the top, at the base. You know, of course it is half, but why? Okay, the answer is, I know you know why, but you don't know how to answer it. The answer is because this is a repeated structure. It is if there is a one single cell here, it is also, there are identical cells at the bottom and at the top of this cell. Betul tak? Ke atas dengan bawah tu mestilah ada bentuk yang sama juga kan? So it is repeated shape. So must be identical. So if it is 1/3, maksudnya dia tak identical lah. Kalau kat sini 1/3, maknanya bahagian atas tu 2/3. So it is not applicable. It is not true for the definition of unit cell. Unit cell must be a cell for the crystal where it may repeat its same structure. Okay, so if it is 1/8 at the corner, why? Because it's surrounded by another 8 unit cell. Okay, over here there are 1 at the right, 1 at the bottom. Okay, mana lagi? Kalau atom kat sini dia connect dengan apa? You know, dia akan connect with another, it will connect with another 7 cell. Okay, at the top there are 4. At the left, right, front, another 3. So this one single atoms will connect. With this one single atoms at the corner will connect with another 7 cell. Okay, so that's the reason it is 1/8. And to complete one circle atoms, it needs to be connect with another 7 cells. Okay, so therefore, so the size of this cell is equivalent to the 2 lattice point or unit cell, or we call it 2 atoms. Okay, the size of atoms. All right, another one. Okay, there are 8 at the corner and 1 solid atom inside. So this one also we call it 2 lattice point or 2 unit cell. Okay, so compared to the primitive structure. But what about the face center? Okay, remember at the face, at the surface, there are half size of the atoms. Okay, so for cubic structure, it contains 6 surfaces. Okay, so 6 multiplied by half plus 1 atom contributed by the corner, so it's equivalent to the 4. So we call it 4 lattice point or 4 unit cell. Okay. So a bit concept check. Okay, metallic iron has a body-centered cubic unit cell. How many atoms of iron are in each unit? So what is the answer?
2.
How you measure it?
Body centered.
Yeah, it's mentioned here, body-centered, and then how you come?
8 corner times 1/8 plus 1 inside.
Yes, exactly. Okay, this inside the unit cell of body-centered cubic, there are 8 atoms multiplied by 1/8 portion of atoms. Okay, equivalent to 1 atoms. And this one, another 1 atom at the center. So the total is 2 atoms. Okay, the total is 2 atoms. Okay, all unit cell structure has geometry of parallel pipe. Basically, it is formed by 6 parallelogram sides. Can crystal have geometry other than parallel pipe? Okay, explain your answer using any household item. Take a photo and upload to forum in the e-learning. Okay, so get this copy of this instruction. I will create the forum in the e-learning, and okay, just a quick take this note. All right, summary. Crystals have an orderly arrangement of their constituent particles. Okay, when we talk about crystal, we always remember this. They have a shape that arranged in order manner. So maksudnya dia akan order tu maksudnya macam peraturan kan. Dia beratur. Alright. So dia beratur ikut susunan yang tepat lah. Okay. So then we assign it as a crystal at a specific structure. In comparison to amorphous solid, okay, kalau crystal, for the crystal means it has ordered structure, but different or opposite to the amorphous, it doesn't have this ordered structure. Okay, crystal structure is composed of a unit cell, a set of atoms arranged in particular way, which periodically repeated in 3D or on a lattice. Okay. Just now we talked about the X-ray equipped on the Curiosity, a machine that goes to the Mars planet. Okay, this machine bring the X-ray analyzer. So they use this analyzer to identify the structure obtained or observed on the planet. So if the material doesn't have a crystal structure, so it is very difficult to the machine to identify, the X-ray machine to identify, because it doesn't have the DNA, the ID for the materials. Okay, so if the amorphous structure observed, it doesn't show any ID from the machine. So that's the reason crystal structure is very important, because it assigns ID to the materials. Okay, there are this is a very basic. You have to know there are 7 groups of crystal system. Okay, and previous lessons come from unit cell which have an internal symmetry. Okay, that's all about the brief introduction on the crystal. So you should be able to imagine. Okay, when there's an atom, okay, you have a metal. Okay, imagine inside the metal there are an atomic arrangement that forming a specific crystal structure. Okay, a specific atomic arrangement. The cell inside the materials, they are different. It can be body-centered cubic like iron. It can be face-centered cubic, for example, like nickel, aluminum, or the gold. Okay, they're even more than that. Okay, different structure. I think that's all from now. For the first part of today's class, let's take a break about 10 minutes, and then let's continue at 4 o'clock. Crystal and polycrystal materials. Okay. So metal, when crystallized, mean when it's solidified into a structure. Okay, solidify, it can be crystal form or amorphous form, but we focus only on the crystal structure. Okay, when it becomes a solid, each one of the atom represented as sphere, and it touch in particular direction and produce a dense packed structure. Okay, regardless of the dimension of the sphere, the structure all will look the same. Okay. So why do metal have a regular lattice structure? Okay, this is because 2 force on cations. Okay, one is attractive force between the positively charged ion and the negatively charged electron clouds. So, for example, this ion, okay, it tends to forming an attractive force between these electrons, maybe coming from these atoms. Okay, another forces, we call it a repulsive force, because these 2 cations themselves, okay, due to their identical charge. Okay, so if we translate it into this schematic graph, okay, atomic force, okay, this is attractive force and this is repulsive force. So this is the atomic distance. Okay, the closer the atoms, okay, what we can see, the repulsive, maknanya positive plus positive, let's say this is positive charge of atoms. The repulsive is what is it? Equilibrium. Okay, repulsive at this direction. Okay, between the atoms is high. This is the stable, we call it. But if the distance is become farther, okay, attraction become the atomic distance. Okay, the next atom is far at this position. For example, the attraction between the atoms is higher. Okay. So until it reach the equilibrium structure, stable structure. So state of equilibrium where both forces compensate each other. Okay, regularity in the atomic structure is called crystal or lattice structure. Okay, during the forming of the crystal structure, it's only a final structure when it reaches the equilibrium structure. So the structure of metal, okay, when we focus only on metal, it consists of three different structure. Number one is a body-centered cubic structure. Okay, it is basically a cubic structure where it has one atoms at the center, and then hexagonal close-packed structure (HCP). Okay, it's forming the hexagonal shape. Okay, like this, roughly. Okay. And then the face-centered is a cubic that having half size of atom at 6 face of the cube. Okay, this is the schematic diagram of the structure for the BCC structure. This is the FCC. If we draw a cubic from this, okay, we can see this is the atom at the face. At the face, okay, there are 6 of them. Okay, we call it face-centered cubic structure. Okay, this one is hexagonal close-packed. Okay, structure of metal. Metal shows different properties depending on the type of lattice structure. Okay, especially when we talk about ductility. All right. If you want to know whether this metal, this category of metal is ductile or hard material or strong materials, basically we always look at the lattice structure. Okay. This is the hard sphere model. This model, it is to discuss the crystalline structure. It is useful to consider atom as being hard sphere with well-defined radius. Okay, this is hard sphere model. Okay, we imagine it is the model says that you have to imagine that the atom having an additive, not additive, like a sphere, like macam bola. Okay, so sebab actually the atoms, right, it's contained of nucleus and surrounded by the what we call electron. Okay. It's not actually a sphere, but when we talk about the model for crystalline structure, we have to imagine this atom having a sphere, a hard sphere structure. So if it is hard sphere, so when we discuss about this cubic structure, all right, 1 unit cell, so we imagine that this inside the 1 unit cell is consists of the portion of atoms that being sliced, and it's become for example at this corner it is 1/8 of the size of this hard sphere. Okay, tak penting sangat pun nak mention benda ni, but I'm afraid that if you are unable to imagine this, so I have to mention about hard sphere. Okay, maybe some of you immediately can relate with the this kind of balls or the atoms in the sphere structure, but some of the students they are stuck with the concept of atomic structure, which is at the center is contain nucleus and there are something flying around it which is known as electron. So they cannot see the shape of this sphere. But the reason I mentioned this is because I want you to see it as a hard ball or hard sphere. Okay. So in this heart-shaped sphere model, the shortest distance between two like atom is 1 diameter of the hard sphere. Okay. What does it mean? So for example, in this example, which is BCC structure, so imagine the distance between this, which is the shortest distance. Okay, we are not just talking about the distance, it is the shortest. Why it's shortest? Because this is a small cell. So it tends to form the stable state. Where it is stable state, where imagine if it is too close until it's overlap between each other, so repulsive energy is high. But if it is too far until it has a very large distance between each other, it is become a very high attraction energy. So in this hard sphere model, the shortest distance between two atoms is 1 diameter of the hard sphere, the shortest. This BCC, the shortest is not 1 diameter. It contains some spaces. Okay. So, but if we look at the simple cubic or primitive cubic structure, the length between this point, the length for this one, okay, this lattice length is actually 2 diameter, two radius or 1 diameter size of atom. That one is smallest. Okay, so if we draw like this, okay, let's say this is 1/8 atom, 1/8 atom. Okay, this is primitive or simple cubic structure. At one side, okay, front side, for example, this is 1/8 of atoms. Okay, for this one, the distance, the shortest distance is the 1 diameter size. Okay, ini jadi dia radius. Okay, 2 radius equivalent to 1 diameter size of atom. This is what meant by this one. This is the shortest one. Tak ada lagi lebih shorter daripada ini. Kalau lebih shorter means it's very high repulsive energy. So for the FCC, the crystal structure atoms are located on the each corner, as well as the center of the tube faces. Okay, example of the atoms. Example of the materials for this kind of structure are copper, aluminum, silver, nickel, and gold. Okay. So if we look at the hard model structure like this, okay, ni yang dikatakan hard sphere model ni. Whatever lah, you don't have to memorize this name of model, but this is the looks of this 1 unit cell. Okay, when we apply the hard sphere model. Okay, if we look at this, all right, this is 1/8 atoms. Okay, multiplied by 8 atoms. And the other atoms is actually half sphere multiplied by 6 because it has 6 faces. Okay, cube face. So it is equivalent to 3 atoms. And this one is equivalent to 1 atom. Okay. So that's the reason the size or the lattice size is 4 atoms. Okay, number of atoms inside this. Okay, inside this cube, this dimension, smallest cube. Okay, occupy 8 atoms inside the cell. All right. All right. Okay, just now you understand, right, how we obtain the numbers of atoms inside the FCC structure. It is contained 4 atoms for the FCC structure. Okay, now from the first information that you receive for FCC is contain 4 atoms inside the cell. Okay, remember this. The number of atoms inside this 1 unit cell for FCC structure is 4 atoms. All right. So do you know this, right? You know this. right, the density. The density is the mass over the volume. Okay, this is a well-known theory. All right. So mass of unit cell, okay, the weight of this unit cell and the volume of unit cell. So when we determine the density of this unit cell, okay, it is applicable similar to the whatever you can relate in this world. Okay, when we want to determine the density, kepadatan, okay, how dense one structure or whatever, okay, in this room, how dense the rooms. You can relate with the amounts of the numbers of items inside the rooms over the size of the room. Another density is the density of the population in a country. Okay, you can relate with the numbers of the numbers of not the numbers, the weights of item, or it can be the numbers of people in the country. Okay, it also can relate to the density. And when we talk about engineering density, it's always relate. When we talk about the density of materials, which is the physical properties of materials, we always relate with the mass over the spaces, okay, the volume. So we cannot say the volume of atom. We say the volume of the unit cell. Because why? Because we want to relate the density of the structure, okay? So when we talk about V is the volume size of this cube, okay? All right. So what is the weight of this cube divided by the volume of this cube? So how to determine this? All right. So based on this concept, you must always know this is represent the weight, the mass, and this is represent the size, okay, the space, the volume, right? So what is the mass that contribute to, what is the thing that contribute to the mass of this unit cell is coming from the atoms inside, okay? How many atoms inside? It is 4 atoms. It is 4 atoms. So the mass of the atoms, okay, this is what is A, okay, before that, okay. So this, okay, this represent the Na and Na at the bottom represent the mass, all right? This is Avogadro numbers. Just a second. Azabda. When we talk about density, of course, density equal to kg per meter cube or whatever the unit is. It can be gram per centimeter cube or whatsoever. It must be a weight unit or mass unit over the volume unit. All right, so if we look at this, N is number of atoms, and then the atomic mass is gram per mole, and the other number is atoms per mole. So basically the mole can be cancelled and atoms can be cancelled. So the final unit is the gram per whatever the size of this unit VC, which is centimeter cube. All right. Okay. So so how to determine? Okay, now we know this is very straightforward, which is N is the atomic number, A is atomic mass, which is gram per mole, or kg per mole, or whatever the unit is. But the thing is, it's a gram. There must be a gram or kg or pound or whatsoever per mole. And this is Avogadro constant, which is atoms per mole. Okay, so this is the volume. So how to determine the volume? Okay, volume is equal to A cube. What is A? This is A. Okay, so the very simple. The volume for the cube is A cube. Okay, so the size A actually can be determined based on the structure of hard sphere inside the cell. Okay, how? We can relate by the diameter of the atom. So therefore, the size of A is highly depends on the radius of atom. The larger the size of atoms, okay, the larger the size of A, which is a lattice constant. Okay, A is lattice constant. All right, so the unit cell is that actually depends on the materials. All right, so for example, nickel has its own size of atoms. Gold has its own size of atoms. So the A value might be different, even though they are all having the same crystal structure, which is FCC. Okay, so here you are going to determine the density. Okay, it is theoretical density. Theoretical density means we calculate actually the density that we determine from the properties of materials. Of course, by experiment, we can use Archimedes concept, but that one is an experimental data. But the density actually, they come up with this very basic calculation. From where? From the smallest weight or mass of the atoms. Okay, how these atoms relates to the density of the materials. Okay, by what we call it? By assume that all the atoms are perfectly arranged. Okay, there is a perfect atomic arrangement without any defects. Okay, macam ada bubbles ke dalam tu, ada porosity ke. That one will slightly deviate the amounts of the density that we obtain from the calculation or theoretical. So this theoretical is how they come up with this calculation is actually like this. Okay, imagine this. There are this one. What we call it, the length at this corner, perpendicular, apa dipanggil perpenjuru. All right, so this length is equivalent to the 4R size of the atoms. Okay, R is the radius of the atom, and this one is A. Okay, this one is A. So apa teori yang kita guna? What is the theory applied for measuring A here? Teori apa No.
Pythagoras theorem.
Matematik kan. Sekolah rendah pun dah belajar kot sekarang.
Yeah.
Pythagoras, yes. Bijak, macam tu. Okay, so sekarang macam mana teorem Pythagoras ni? Awak tak boleh reka-reka lah. Okay, it is very basic. Which is, macam mana nak relate So the 4R kuasa 2 equal to A kuasa 2 plus A kuasa 2. This is A, this is A. Okay, this is 4R. Okay, Then we got this. Macam mana nak buat? Cuba try sikit exercise matematik zaman kanak-kanak dulu. Adakah you akan dapat A equal to this? You should have. Kalau you tak dapat, something wrong. Go back, open the textbook for the primary school. Okay, what is the basic concept for the theorem Pythagoras? Okay, then you get this. A equal to this R. Okay, how we can relate between air and the size of atoms. A equal to berapa ni ni kalau convert tak payah ikut nombor lah. Mana nak 2 multiplied by square root of 2 multiplied by R. Okay. 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 Now, for N, we know it is equivalent to 4 atoms for the FCC. This one we can obtain. Okay, the atomic mass, it is a standard, not standard, it's a constant. Okay, the mass for the each element that you can obtain from the periodic table. Okay, and the Avogadro constant is 6.022 multiplied by 10 power of 23. And then this one is constant. The NA is constant. And then A is relates to the R. Okay, the size. R, of course, the size of atoms is a constant. Every element in this world has its own size. Okay, which is a constant. Okay, you don't have to calculate. It is a constant that available in the periodic table. Okay. All right. Okay. Okay, the copper has atomic mass. This is the atomic mass, which is the A value, and the radius 0.1278 nanometer. Calculate the volume density. Volume density means that the crystal density lah. So remember, okay. So let's do it together. Don't be lazy. Find a pencil or pen and a paper, or you can use your tab or whatever devices. So remember, the density is equivalent to the mass divided by V. Ni well known, jangan tak tahu. So further derive this equation, and we can obtain from, remember this is FCC, N equal to 4. And A over the volume of cell. Okay, number of and the Avogadro number. Okay, so now we know that N equal to 4 atoms for the FCC. How we obtain this? It is coming from the 1/8 at the corner of the atom. They have 8 corner plus 1/2. Okay, for the 6 cube faces. So it is equivalent to 4 atoms. All right. So, and we know the value A equivalent to 63.54 gram per mole. And then Avogadro number is 6.022 multiplied by 10 power of 22 atoms per mole. Okay. So what is the V equal to A cube? And then if the question, but this question doesn't ask you to derive the relationship between A and R, so you don't have to derive it, but straight away you can calculate this by 2 square root 2 R cube, right? So we know that the value of R is 0.1278 nanometer. Then you can calculate. So what is the value for V? Cepat. Siapa dapat?
Doktor, Avogadro number tu tak perlu NA.
Belum lagi, baru nak cari V.
Okay.
Boleh? Ada tak? Berapa? Kuasa 3 tu volume. Selalu student kalau tertinggal, dia dah excited sangat, calculate. Sebab senang kan? Jadi kadang-kadang kita terlepas pandang benda yang macam ujung-ujung tu. Kuasa 3 ke, yang paling luar tu.
It's 0.047.
0.057.
47.
47. Okay, this one is nanometer cube. Is it? You straight away use this, or it is equivalent 0.047 multiplied by minus 27. Is it?
In nanometer.
Yes.
Betul lah kan? Nanometer tu you tak convert kan? You direct tekan calculator nombor tu kan? So tak apa. Kita teruskan lagi. So now the density is equivalent to n equal to 4 multiplied by 63.54 gram divided by 0.047 multiplied by 10 minus 27 multiplied by 6.022 then 23. Okay, so this one is meter cube. Okay, so you can use another units which is centimeter cube. Sometimes the density is in the unit of gram per centimeter cube. Sometimes kg per meter cube. Okay, right. So what is the answer? Let's say we use the gram per meter cube. Or you can use a kg per meter cube. Apa jawapan dia?
8.98 megagram per meter cube.
8.98
Gram per meter cube.
per
Meter cube.
meter cube. If you convert it into okay, this one is 8.98 times 6 power of 6 times 6 minus 6 gram per centimeter cube. So this one, this is 8.98 gram per centimeter cube. Okay, now let's Google the density of, just Google density of copper. What is the value? Just Google from the internet.
0.96.
8.96. So it's slightly different, right? 8.96, okay, theory value. Theory value is 8.96 gram per centimeter cube. Right, it is slightly but acceptable. The theory is applicable, and remember during the determining the real density of the materials, we use a standard procedure of the experimental where we it can be used by using weighing the materials by using the balance. Okay, there are so many factors that influence the weight of the materials, even though we are using a very high sensitive machines. But remember, the materials that we weight, we measure the dimension by using a very accurate measure device, but still to produce that one solid standard material to be tested, maybe there are some defects inside. Okay, maybe there are missing atoms in the atomic arrangement inside the material. So that's you cannot get an exactly 8.98 gram per centimeter cube. So, but it is only different at very small percentage. So meaning that the theory is applicable, meaning that the theory of our crystal structure is close enough to the real application. So if this is the question appear in the test or the exam, and you got the answer 8.96, so meaning you Google the answer. So remember that, okay? So it is always slightly different from the real experimental value, okay? So next, okay, think if I arrange this orange and the basketball in their respective cubic boxes according to FCC unit cell, will the percentage of sphere volume occupying the respective space be any difference? Faham tak maksudnya kalau kita susun elok-elok naklah ni, adakah bahagian sphere, is it that the amount of orange or the ball that insert in the cubic space is similar? What do you think? Will it be similar?
Tak faham sangat lah.
Tak faham sangat macam ni bahasa Melayu lah saya translate. Saya pun first time terbaca statement ni. Alright. Fikirkan jika saya susun orange ni dalam dan basketball ni dalam dia punya box masing-masing, yang orange tu dalam kotak orange lah, yang basketball ni dalam pagar dekat shopping mall tu lah. Okay, container dia tu. Adakah percentage sphere volume bagi orange ataupun bola ni berbeza volume yang masuk dalam kotak tu ataupun masuk dalam sangkar tu akan menjadi berbeza kalau berbanding dengan keadaan tak bersusun ni. Okay, kalau kita tak susun dengan kita susun. Saya bagi contoh lain lah, you tak faham kan. Okay, nampak tak? Saya share. My entire screen. Okay, sorry. Ni apa ni? What is this?
Weh,
Kuih apa ni?
Kuih tart.
tak nanas.
Tak nanas. Kuih raya. Ini kuih sebelum raya namanya. Right, tak nanas ni. Ya, awak tengok dalam ni dia bersusun. Kalau lah dia jual ni, berlambat-lambat tak bersusun macam ni, awak agak-agak bilangan dia sama tak? Do you think if the seller does not arrange this tart, okay, inside sorry. Okay, let's say the seller does not arrange it properly like this. Okay, they just randomly put all this this biscuit inside this container. Do you think that the amount will be different? What do you
Yes.
think?
Yes.
Which one do you
Yes.
think?
Different, Doctor.
Would you like to have this one or the non-arranged biscuit?
Orderly arranged.
Arrange one.
Why do you think you need to have this well-arranged tart?
Optimize space.
Optimize
Save
space.
space.
So meaning that the numbers of biscuits is higher if they arrange like this.
Yes.
Yes.
So similar to the example that I've shown just now, okay, if they just randomly arrange the orange inside the box, maybe the amounts, because they will generate more empty spaces, okay. Let's say this one, if there is a missing tart at the center, okay, if there is a missing tart at the center, the next layer of the tart or the biscuits at the top layer will be not arranged properly, and it will create more empty spaces or vacancy inside this container. So this is what I meant. So congratulations, now we chose a right answer. So okay, let me continue with this the slide. We have about 6 minutes to finish our lesson. All right. So another topic, another lesson you need to understand is the atomic packing fraction. Okay, atomic packing. How to pack the atoms inside. This one we are not using the unit of mass. Okay, we just consider the numbers of atoms inside the space. For example, the number of items inside this room. If this is so many items inside my room, so my room will become very packed. Okay, very packed. So this is what meant by packing factor. So packing factor is can be translated how much the space occupied by the sphere over the space, the size of the space itself, the volume of the unit cell, the volume of this cube. Okay, so the volume of the sphere, okay, is we can calculate by the size of the sphere. Okay, ni adalah rumus. This is the equation for determining the sphere, the volume of a sphere. Okay, and then we have the 4 atoms inside the FCC structure. And again, the V, remember V of the cell equal to the A cube. So this one we have defined just now. So if we calculate this, right, this is R3. The R is can be cancelled top and bottom. So actually the pack, how pack the cell, okay, we can determine, okay, by using this equation. All right, by we can eliminate R in the equation, and we will obtain the FCC structure. The packing factor fraction of this structure is 0.74. Okay. So another element that you need to consider is the coordination number. Okay, the total is a total number of nearest atoms for each atoms inside the FCC structure. Okay, for example, the brown atoms is connected to several atoms nearby. Okay, the blue ones will connect. This is our coordination number. Means that these brown atoms will connect with the 4 at this lattice, and another 4 at this lattice direction. So this another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 coordination numbers. Right. I think I should stop until here before we proceed. It's basically for the BCC also similar, but I will explain further in details for BCC structure. It is if you can just browse through the the slide, it is actually similar to FCC in terms of when we want to determine the number of atoms inside. Okay, the numbers of atoms inside the BCC structure. Okay, it is equivalent to the 2 atoms. Okay, so if we apply the Hartsfield model, this is how the Hartsfield model looks like for the BCC, and 8 at the corner and 1 at the center. So it is equal to 2 atoms for this model, which is BCC structure. And for density determination, it is a bit tricky, but it is not so difficult. Because why? Okay, how to relate between A and R? Okay, okay, R is the size of atoms, the radius of the atom. So it is easy, all right? So we know this is A, this is A, this is A, all the lattice equivalent to A. Okay, all these lattice are A. So first, what we have to do, we determine this value first. How? Because we know this is A. So this, the length of this part is equivalent to A square plus A square root, this guy. So this guy, okay? So it is equivalent to 2A, and it is square root 2A, all right? So this is the length of this part. And then we know this is A. So we can use the same concept, theorem Pythagoras, to determine this one. Why we want to determine this length? Why? It is because it's equivalent to the 4R. So we want to relate between A and R. So we need to relate between A and this length. At this corner to this corner. We cannot directly use A because first we need to get the length at this bottom. Okay, this bottom. And then this one is equivalent to A. Okay, A. So next, we can have a relationship between A and R, where this is the relationship between A and R. Okay. So next, what you have to do, you need to find the APF and coordination number for the BCC. Okay, so find it yourself, how to determine the close-pack value, APF value for the BCC. Okay, and later I will explain a bit on the HCP. Okay, let's stop our class for today. See you again next week. For those who not yet joined the e-learning under my section, please let me know. I will manually insert you. And I think that's all for today. Any question?
No,
Doctor,
doctor.
we see next week.
Apa dia?
Tak ada kelas Rabu kami tak?
Rabu ada. Next week, saya cakap next week. Sorry, next class.
Alright.
Tak ada soalan? If you have no question, class will dismiss. I think that's all for today. We will continue next Wednesday for 1 hour class. And